Hello, my name is Gennady Staskevich and my presentation today is on YOLO. So what is YOLO? Well, YOLO is a fast real-time object detection classifier designed to detect generalized objects, categories. By generalized, what we mean is that instead of detecting a car, more specific would be Ford Mustang, Ford Focus, Honda Accord, Honda Civic, or a Chihuahua versus a dog. So this is designed for detecting more generalized categories like a car, a dog, plane, boat, and so on. This approach is based on deep convolutional neural network, and it's using it as a logistic regression classifier, both as a classifier and as well as the region of the object itself. And what I mean by convolutional neural net is essentially consider this plane right here is the input data, like an image or something. And what kernel, which is the convolution part, is essentially an n by n set of neurons, like 1 by 1, 5 by 5, 3 by 3, and so on. So it acts as a filter over the input data. So an analogous example or something similar example would be taking a red filter and applying it to a camera, so it only sees now red, sensitive to the red type of data that's coming in, or green or whatever. So it's very similar concept, is that it makes that particular cell so it passes the information that is sensitive to that particular filter. So YOLO was presented at NIPS 2015, and NIPS stands for Neural Information Processing Systems Conference. This is one of the premier conferences for any neural-related research. This particular work was heavily inspired by GoogleNet project, which introduced the inception module, and at the time it's believed to be the best. I recall it was the best performing classifier. So this GoogleNet the name actually references the young Linet's original inspiration for deep learning. They introduced this in this paper, this inception module, which was used to produce dimensionality reduction across multiple filter scales, like 1 by 1, 3 by 3, and 5 by 5. This particular work did remarkable, very good performance, but it was computationally expensive. So this paper, YOLO paper, that's presented, this is a link to this paper, and the project page is linked to this. There's a link right here. The paper is currently on its 5th revision, and project is already having its 3rd major revision, which essentially includes more optimizations and supports more object categories, more specific categories. So in reality, this particular presentation covers the first edition of the paper. So in this paper, they actually released 2 versions of YOLO, just YOLO and Fast YOLO. And the YOLO targets 45 frames per second, while Fast YOLO is capable of pushing 155 frames per second, which is remarkably fast. And to achieve that, they require a GPU Titan X, which is consumer on a high-end consumer graphics card. By real-time systems, I think they consider 30 frames per second. And so what makes YOLO fast? In essence, it's the approach that they use. Essentially, they used one single convolutional neural net to do both the category identification and the object box identification, and assigning the probabilities to those. So it's a single neural net that does all this. So how does it compare to other approaches? At the time, I believe it was the fastest system for object detection system. It's significantly faster than other approaches. So, and why is it faster? Because typically other approaches would take an existing well-performing classifier, create pipeline around it, and essentially this resulted in more computational overhead, more steps, and but at the same time it was the performance was good. So with respect, I think at the time, deformable parts model (DPM) was the only real-time system that was able to run 30 frames per second and at 100 frames per second. And one of the drawbacks behind this DPM model was that it only looked at local regions, so it didn't take the entire image or the entire contents of an image into a context. So it had poor performance, poor accuracy, and it had the following. So they had strict feature extraction, classifying regions, predicting bounding boxes for high scoring regions, but that was still resulted in poor performance. And at the time, I believe YOLO was the fastest object detection for the Pascal dataset. So the DPM was way too slow by 2 orders of magnitude to be a real-time system. Let's see. No, that was sorry. That was so the recurrent neural net, recurrent convolutional neural net minus R. They used static bounding box search, and it resulted also similarly to the DPM model in poor accuracy, but the performance was just terrible in that one. It was 2 orders of magnitude slow. Then the FAST, another revision of that used convolutional neural net, used so they made some faster used again another neural net for identifying the regions, but it was still too slow. It was taking about two frames per second for each frame. So and another faster version of that called faster CNN, it was still slow compared, relatively still 2.5 times slower than the YOLO paper. And another point is that the reason why we're comparing to the fast recurrent neural nets is that this was at the time the best performing object classifier for moving for video. And also the YOLO is much better at detecting false prediction of when there's nothing to detect. So it had a lot less false positives, because I think one of the reasons that authors give was that because of the global context that YOLO it takes into account when doing conditional probabilities of each segment. So one way to measure accuracy of the systems is intersection over unit measurement and mean average precision. So the intersection over union is one way that takes a rectangular region for predicted class, the location of it, and then it takes the ground truth. So all the pixels in the predicted class are essentially measured the intersection of the predicted class between the predicted and the true set divided by the union of those two sets, the predicted and the truth, ground truth set. So this would give you the intersection over union measurement. And then the mean average precision is used how well a particular algorithm scores across or averaged across all the classes that it's able to detect. So those are two measurements. So how good is it? Well, the comparison in this slide shows that for real-time systems at that time, they only found the 2 DPM models, were 100 Hertz and the 30 Hertz model that was trained on a 2007 data set, Pascal data set, and that data set, essentially the 100 frames per second, the DPM model was, accuracy of the DPM model was just terrible. It was 16%. Um, uh, and the 30 hertz DPM model had the better accuracy at 26%, but it's still far below the anything useful. And the frames per second, obviously 130 respectively, but the accuracy was way too low. So YOLO, on the other hand, if we look at it, with fast YOLO, which used reduced fast difference between fast and regular YOLO was regular YOLO used 24 layers in a network, and fast YOLO used only 9 layers in a network, convolutional layers. So fast YOLO had poorer accuracy, 52%, but it was running at 155 frames per second, more than doubled, almost more than doubled in performance. Actually, did more than double in performance than the 30 hertz DPM model. And while running 5 times as fast. And YOLO actually had 63.4 mean MPA, or mean accuracy precision, and running at 45 frames per second, which is quite remarkable at the time. So how does YOLO compared against systems that were less than real time? And in comparison, recurrent convolutional neural net minus R was able to run, actually had pretty good classification, 53.5%, but only 6 frames per second. And the fastest DPM model had 30% mean accuracy precision, but YOLO on average didn't perform as high as some of the better approaches. So there is a trade-off. I mean, between precision and how fast you can run things, but still the performance, the YOLO's performance was remarkably better, and so the trade-off possibly seemed reasonable. In terms of error analysis, the major thing was that YOLO had a difficulty with object localization, which accounted for the majority of the errors combined, if you take all the other errors. So if one were to define a little better object region, that would significantly improve YOLO's performance. Another thing, that YOLO had very low rates on detecting areas when there is no objects. So that was a very good thing for it. So it had much lower false positive rate. So here's another measurements for mean accuracy performance measurements over the Pascal VOC 2012 leaderboard data set across all the 20 categories. And the categories you can see right on top, and this is the mean accuracy performance score. And so some accuracy, some labels had very high accuracy scores in high 80s, 85, 83, and some had actually very poor performance, such as 43, and so on. And let's see, what I think the 43 is the lowest one, 65. So other classifiers, as you can see, YOLO scored in terms of mean accuracy performance closer towards the bottom. Nothing remarkably, I mean, still reasonably well, but considering that it's running at real time, so and the actual performance, the deltas between the best performing and its current is reasonable, but not so terrible, considering that it's able to run at real time. and with reduced false um, detection rates, with less false positives. So overall, it's actually a pretty decent system. And one of the things authors also did was they combined YOLO with fast recurrent convolutional neural net, and they essentially used YOLO for predicting the background performance, and used fast recurrent net for the localization. So this is the system that actually came out fourth from the top in terms of overall performance, and actually had pretty close to the categories. So actually, several categories. It beat the highest performing model. So it actually reached 89% on some of these things. 89, 82, 87. And so these two were tied. Uh, so there is definitely something that YOLO has that was state of the art at the time. So in addition to the being um, the fastest running classifier. So what are the limitations? Well, the way that the architecture is designed is because there is multiple downsampling, there is going to be fewer generalized classes, and also another limitation is that strong constraint on number of nearby objects that can be detected, because there is part which will go into more detail of the actual algorithm. Um, the way that YOLO does is it takes an image and divides into a grid cells, and then each grid cell is responsible for two boxes, that it predicts two boxes in a single class. So there is actually a limit on number of objects they can detect. And also another limitation is the loss function treats the error the same way regardless of the size of the prediction box, meaning that if you have a large detection box and a small error, then the error is negligible. But if you have a small box and you have a small error, then this particular error will have a significant impact on the IOU calculation, the confidence score, which we mentioned earlier on, this calculation right here, the intersection over union calculation. So what does YOLO architecture looks like? If you take the GooglyNet architecture design and look at both YOLO and that design, you'll see that it does share a lot of there is a lot of similarities. However, the difference is that this particular architecture does not use the inception modules that were introduced in the convolutional neural net. Okay, so similar to what they do in this particular, they use in YOLO use one-by-one convolutions to reduce the feature space into each additional layer. So let's see. So what does this algorithm look like? So the first step is images sliced down or broken down. No, the first step is actually image is reduced to 448 by 448 pixels. The second step is slicing an image into a set of grids, into a set of slices or grids, blocks, which is S by S. Next step is this step happens simultaneously. So each grid or each box in a grid computes two prediction boxes or bounding boxes for objects, and also simultaneously each box has a confidence score, and the highest confidence score within a particular box or region actually wins, is chosen. So there five values are being predicted here. So we predict a box, the position, relative position, and then the width, the height, and the confidence score. So those are 5 values that are being predicted. And for the paper, they use the S for the slicing, they use 7, B for number of boxes to predict is 2, and C for number of classes that the framework supports is 20. So their final tensor is 7 by 7 by 30 for the prediction. So the YOLO algorithm uses so the confidence score is the intersection, or as we mentioned earlier, intersection over union between the predicted bounding box and the ground truth. This is their confidence score. So each grid cell, as we shown in the earlier slide right here, each grid cell, and there would be, in our case, 49 of them because it's a 7 by 7 grid. So each grid cell calculates conditional probability of a class. Probability of a class given an object. And this is the formula we use. Probability of class equals probability of class given an object times probability of an object. So while we detect two bounding boxes, but only one class and one bounding box is chosen, and only if that particular confidence score is reached over certain threshold. Okay. So again, this is one of the limitations that actually, or cause of the limitations that I mentioned earlier. Oh, what did I just jump? So in essence, this particular algorithm, it does remarkable at runtime performance. So it does both the bounded box identification, computes the conditional probability of other classes in nearby vicinity, and then considers the objects. So it generates this particular class objects. Um, However, it does suffer from, as I mentioned earlier, some limitations in terms of accuracy. But the performance is remarkable because it's a single neural network that does all these. The entire pipeline is within the captured within the network itself. So the conclusion is this algorithm is extremely fast. It does really good job at detection general objects. So applications are very useful for fast object tracking, navigation, possibly even vehicle navigation because how fast it runs, and it has fewer false positives. But it can certainly benefit from more newer approaches that have better accuracy. And thank you for your time. If you have questions, comments, please do not hesitate, email them to me. Thank you.